So here's our second example of hypothesis testing. And this time, rather than a one-tailed, it's going to be a two-tailed test. It tells us that here in the question, but we'll also see why in the question we could have known that it was a two-tailed test anyway. Okay, so let's have a read through. So a psychologist is researching short-term memory. A pupil is presented with a tray of 10 objects and asked to remember as many as they can when the tray is removed. If we were in school, we might have actually done this as a little practical, but anyway. So 10 is important, that's going to be our n in our binomial. Over a period of several weeks then, the psychologist ascertains that the proportion p, so the probability of success here, of objects remembered is 0.35. So this person's successful 35% of the time. They get 35% of the objects over time correct. The pupil then takes a long holiday, and the psychologist wants to see if there's any significant change in the value of p, so in the proportion of objects remembered when they return. Okay. Now the fact that it says change is really important here, and you'll see that I've underlined that, because change is what tells us, that word tells us it's a two-tailed test, because this person might get, when they're away and they come back, they might get better at the test or they might get worse. It doesn't say it's an improvement or a decrease, so it does not increasing at one end, it's not decreasing. We just don't know. It's just saying, is there being a change? Okay. And if you think about it, when this person comes back from holiday, they might have got worse at this test, at this game, because they've forgotten what they were doing, or they might have got better because they've had a rest and they've come back to it refreshed, or there might be no change at all. Okay, so that's what we're going to test, whether the psychologists can test whether there's been a change in the success rate of this. Okay. It asks us to find critical values for a two-tailed test at the 5% significant level. So they're asking us to say basically at both ends, at the lower end, how many would this pupil have to get right for there to be a negative change, a decrease, for them to be getting worse at the test? Or alternatively, how many would they have to get right at the upper end to say actually there's been an improvement in this proportion? Okay, so let's write down what we know so far. Let's write down the information in the question, but let's write it down mathematically. So first of all, let's define our random variable. So our random variable here, x, is going to be the number of objects remembered. Okay, and x here is binomially distributed, remembers an item or he doesn't. So 10, number of trials, 10 objects, how many of these do they remember? And our probability of success here is 0.35. The proportion they get right is 0.35. Okay. So our null hypothesis is that nothing's changed and this stays the situation. So our null hypothesis is under this binomial distribution, the probability of success is just our 0.35. Our alternative hypothesis here then, what the psychologist wants to check, is if there's been a change in that proportion. So our alternative hypothesis is that the probability of success, P, is now no longer equal to 0.35. So not equal to 0.35. So you'll notice here it's not a greater than, it's not a less than, it's just any change at all. Okay. And we're asked to do a two-tailed test at the 5% level of significance. And this is important because it's two-tailed now. We need to split that 5% between the lower values and the upper values. So it's actually going to be 2.5% for each tail. And this is sometimes where people go wrong, because sometimes people do 5% at the top and 5% at the bottom, but that would give a 10% level of significance for the test overall. So just be careful of that. If it's a two-tailed test, split that level of significance between the two tails. Let's think about this on a number line then. So the worst case scenarios, I don't remember any. Best cases, I get all 10, so between 0 and 10, that's what's happening with my values of x. And what I'm looking for here for a two-tailed test is I'm looking for critical values. So I'm looking for a value here at the bottom end, I'm going to call it C1, where if I get this amount of objects right or less, so this amount or worse, then the probability of that happening is not very likely underneath this situation of a binomial with p is 0.35. So I'm looking for this probability here being less than or equal to C1. I'm looking for this to be less than or equal to my 2.5%. So that's what we're going to have a look at doing in a second on the calculator. Okay, because I'm saying if it's critical, if it's down here, if I don't get very many right at all, whatever the value is down here, that wouldn't be likely to have happened just by chance, and something's got worse. I've forgotten how to do the test. I've got worse at doing this game. Alternatively then, at the top end, so some value up here, another value, let's call it C2, if I come back from holiday and I get C2 number of objects right, or better, then I'm going to say if I'm in that region, then again, something's changed while I've been away, and I'm now better at doing this. My proportion of success has increased. So here, it needs to be unusual. It needs to be out of the ordinary. The probability of being in here needs to be, for this particular test, less than 2.5%. It needs to be not very likely. So anything in the middle here, we're saying, well, that could have happened anyway. If I'm down here, really unlikely. I'm up here, really unlikely. So something's changed. So at this top end, I'm looking for the probability of being greater than or equal to some value here. I want that to be less than my 2.5%. So as a probability, 0.025. Let's have a look then at these two sides of this question. So the less than or equal to, it's going to be a binomial CD. So let's just go back into there, binomial CD. I want my list now because I don't know the value of the variable. I don't know the x value. So I want it to list a few values for me so I can see which one I want. And you'll see that I've already typed this in. I've typed in 0 to 10 because there's 10, n is 10 here. If it was bigger than 10, if n was 100, I wouldn't keep typing into 100. I'd maybe do 10, 20, 30 and try and reduce the numbers that I want so that I can just keep doing sort of trial and improvement to find my values. Okay. Looking at this then, n is 10. My probability of success is 0.35. And then it'll work out the list for us and it tells us these probabilities. I'm looking for the first value of x, so the probability is less than or equal to 0.025. And I don't know if you can see that on the screen, but here the probability of being less than or equal to 1 is 0.0859, so that's too big. The probability of being less than or equal to 0, that's the first one that works, and that's the only one that works here actually, 0.0134. So that means this value here is actually 0. Why? Because my probability from my calculator being less than or equal to 0 is the first one that's less than 0.025. And write that down in the exam so the examiner can see exactly what you've done. You've got evidence for your answer. So that means my critical region then here is x is less than or equal to 0. So in actual fact, I'm right down here, right at the very bottom. So in this case, because 0 is my lowest value, I could actually say, well, that just means x is equal to 0, but either of these is absolutely fine. Okay, let's look at this top end. So at the top end now, the slightly more difficult situation where we've got a greater than or equal to. So don't forget your binomial CD on your calculator will only give you less than or equal to probabilities. So I'm going to need to do a 1 minus here. So 1 minus the probability that x is less than or equal to something. Well, this bit that I want here, greater than or equal to this value C2, is exactly the same as 1 minus all of this bit. And because it's discrete, greater than or equal to 9 is the same as 1 minus less than or equal to 8. Greater than or equal to 7 is 1 minus less than or equal to 6. So this value here is 1 less than C2. So if I want to be greater than or equal to C2, that's the same as 1 minus everything less than or equal to C2 minus 1. Let's do a bit of rearranging. So bring that across, take that across the other side. 0.975 is less than or equal to the probability that x is less than or equal to C2 minus 1. So reading that probability this way, the probability that x is less than or equal to C2 minus 1 is greater than or equal to 0.975. And again, I want to look at my table. I've kept it on here from before. I'm just going to scroll down. And I'm not sure if you can see, but here 6, so the probability of being less than or equal to 6 is 0.9739. Now that's no good because it's not greater than this. It's quite close though, and in some questions it might say pick the value that's closest to this two-tailed test of significance. And if it said closest, then I'd choose 6, but this one doesn't, so I need to be greater than 0.975, and the first one that does that is 7. So here, probability of being less than or equal to 7 is 0.9951. So I'm just going to write that here as my evidence. Less than or equal to 7 is 0.9951. So there's my evidence for my examiner. What does that mean then? It means that this value, C2 minus 1, is equal to 7. So rearranging, C2 is 8. So as a critical region, my X value must be greater than or equal to 8. And they're my two critical values, my critical regions. What does that mean then? It means then, if this person comes back from holiday, they do this game again. If they get none right at all, they don't remember any of the objects when they're removed, then the psychologist can say there's evidence at the 5% level to say that there's been a change and that actually this person's got worse while they've been away. Or alternatively, this person comes back from holiday and gets 8 or more, so they get 8 or 9 or 10 of the objects correct. Then the psychologist can say at the 5% level, two-tail test, there's evidence to say that actually they've got better at this while they've been away. And that's the significance of these two in this particular question. Any other value then in here, so if this person comes back from holiday and gets 1, 2, 3, 4, 5, 6 or 7 of these objects right, then there's no evidence at this 5% level that anything's changed, and they might have got those sort of values anyway just before they'd even gone away when this hadn't changed in any way at all. Okay. So that's hypothesis testing finished, and that is actually the very last statistics topic in the AS level. Now, it is quite a difficult concept, this, so once you've had a look at these two videos, you've maybe looked at the other PowerPoint, you've had a look through the book, give the homework a go. Don't worry if you can't do it. When we're back in school, this is one of the topics that we'll recap and go over quite a lot. Okay, have a good Easter.